Good afternoon. My name is Rakhim. We're going to talk a little bit about quantum computing. I work as a software architect at this company called IQM. Its actually headquarters is just across the bay in southern Finland. And I'm fortunate enough to be at one of those rare companies that actually do the full stack quantum computing thing. We build everything starting from the actual chips and then all the hardware that needed to operate the chip, deliver it on site, and then write all the software starting from low-level firmware to drivers to high-level quantum programming SDKs. So I'm not a physicist, I'm a software engineer. I will try to convey as much as possible of exciting things that I learned over the years and I'm still learning. And this talk will be like highly simplified. You can imagine talking to a person maybe not too involved in Python or programming and saying things about, the interpreter, about the databases and APIs and the garbage collection, trying to explain something, but you know how much of depth actually under each of that statements. So here will be similarly simplified statements and lots of depths. But my goal is to kind of give you the big picture so that if you are interested in something to know a bit more in certain areas, then you know basically where to look or how to Google things. So imagine you have a list of numbers. It's unsorted, and you're looking to find an index of a particular number there, let's say 12. Classical computer science tells us that, well, the best you can do is to try. It's unsorted, so you cannot do any searches, and at worst, you will have to go through all of them. You're really unlucky. You always find your number as lost. Now imagine you take this gaming die, this six-sided thing that you use in board games, and you say, whatever it gives me, that would be the answer. This is useless, right? It just gives you random numbers. If it's a normal die, all numbers are equally probable. So you keep throwing it and it gives you random numbers, and you're saying, well, this isn't helpful. This is a quantum computer that is not calibrated, so it doesn't operate very well. And you did not program it well. You did not write a quantum program well enough. Now take a leap of faith with me and imagine this kind of magical scenario where you take the same gaming die and you slightly modify it. You maybe add a piece of material somewhere, like cut a corner, make one side more weighted, and you do it in a way that is somehow connected to the data, to that list of numbers. You still don't know the answer. It's not trying to trick this cube to go in the correct answer. You don't know the correct answer. But you know the shape of this list, you know some other properties, and you somehow make the cube different so that it's still random, but less so. It's less random. If you throw it multiple times, it tends to gravitate, to be skewed towards a certain number, which happens to be the correct answer. This is kind of crazy, like this doesn't make sense. But this is basically how a quantum computer that is well calibrated and well programmed by the programmer works. If you don't take anything else out of this lecture, take this. It's a very remote analogy, but quantum computing is basically trying to trick the universe in some isolated little piece for a very, very short period of time to behave slightly less randomly in a productive way that is useful to you when you solve some problem. So with that in mind, here's the plan. It's very thick, it's very dense. Buckle up. We start with quantum physics, we have to, but then we go into quantum computing, then into particular one kind of quantum computing, and then into its ecosystem and the full stack programming and Python. And hopefully, if God's allow, we'll do a short demo. This is an artist's rendition of a distant exoplanet with the coolest name ever, WASP-39b. It's about 700 light years away from Earth. For comparison, Jupiter is, I think, like 35 minutes away. So this is really far. It's so far that we have to look at this rendering because if we look at the optical telescope, we at best see this smudge, like this pixel. You cannot see a planet. However, if you Google this planet, and many other exoplanets for that matter, you will find some publications where they say, wow, we actually found sodium, potassium, carbon dioxide, carbon monoxide, and different elements in the atmosphere of that planet. How? Like, you cannot see it. It's just a pixel, yet you know what kind of molecules are in the atmosphere of that planet. And the answer to the how question is spectroscopy. It's that thing that takes advantage of a peculiar property of some quantum objects. So scientists discovered this about more than 100 years ago now. If you take some atom, for example, this is sodium, it has 11 electrons, and you shine a light of wide spectrum, different, it's basically photons at different frequencies. Low frequencies, red color, high frequency, violet color. You shine the light through the through the atom, and you look at the light on the other side, and you notice that some parts of the light are gone. There are these black bars. And it turns out photons of a certain frequency got absorbed by certain electrons in that atom. The energy of that photon went into the electron and made the electron move to a certain energy position. Basically, got the energy from the photon, got excited. And as a result, the light on the other side does not have that photon. You don't see those colors. And this kind of looks like a barcode, and it is a barcode. It is a unique identifier, like a fingerprint of this material. Once the electron goes into that high position, it usually wants to go back down. When it does spontaneously, then it re-emits the photon of the same frequency. So later, you see another bars, which are like the inverse of those. So we have all those elements on Earth. So the scientists did this experiment for the whole periodic table and got like fingerprints of various elements. And now we have the database. And then they used multiple special instruments on the James Webb Space Telescope. And they caught that exact moment when that exoplanet was in front of its star, so that the light going from the star went through the atmosphere, and they looked at that light, and they found that bars in that light, and now they know what kind of materials are in the atmosphere. So this is amazing. And if we could simulate this, that would be great, because, well, not only to look at photons interacting with electrons, but if we could simulate any kind of quantum interaction like that on a computer, we could, design new drugs, new car batteries, agriculture elements, stuff like that, without experimenting. We can just simulate it. And from my simplified description, it seems like you can simulate like there's a state, then it takes the frequency, you just compare the frequency. If it's the correct one, you move the state to 1. And when scientists started to think about these things, they realized that it's not that simple. Unfortunately, the state of any quantum object is not discrete like that. It's not just 0 and 1. It's actually must be described by a more complex formula that happens to be the same formula that describes waves, like water waves or sound waves, these things. And it turns out that for a system that can be observed in one of two states, like this electron, not excited, excited, 0, 1, what you're actually looking at is a probability distribution. So these numbers in front of 0 and 1 in these weird brackets called probability amplitudes. And we can think of them as basically probabilities. You derive probabilities out of them, and they have to sum up to 100%, because in the end, when you look at the electron, it's either there or there. It's never in between. You never see the wave. But in order to actually model this thing reliably, you have to have that state. You have to have these complex numbers that describe the probability. So even in the 50s, they started thinking, okay, we actually would benefit from simulating these quantum things. And they quickly realized that the computers are not fast enough. But even today's computers are not fast enough. So they weren't thinking about, how a computer in 20 years could behave. They just thought how a computer in principle could behave. And there's actually a physical limitation of how powerful a computer you can build in this universe. A normal computer, I mean. And it turns out if you imagine the most powerful computer ever that uses all of the atoms in the observable universe, you have this limit. Like, this is how much you can compute. This is how much memory you can have in the whole universe. And then if you look at a sufficiently complex quantum interaction, like different molecules interacting with some fields and lights and stuff like that, if you want to simulate that, this hypothetical super big computer will not be enough. So what do? Feynman and his collaborators in the 50s already started to say that we actually have to build kind of quantum computers that actually operate on those states directly, not as ones and zeros, but as these waves. And this brings us to the idea of quantum computing. So before we go into practicalities, let's imagine we can build a quantum computer that instead of a memory where you can have a 0 or 1, it has something similar to that electron that could be in this position or in this position or in a superposition that is described by these probabilities. It can be, popular science likes to say at 2 places at once, which I guess maybe 2 states at once, but it's kind of tongue-in-cheek because, well, that when it is not 0 or 1, it's not simultaneously 0 and 1, and it's not undecided. It's just a completely different state. It's like saying that gaming die with the 6 sides, when I look at it on the table, it's in one of 6 numbers. It cannot be in any other state when I observe it. But when I throw it in the air and I ask, what is the state? Well, you can say it's like 1 and 2 and 3 and 4 and 5 and 6 at the same time, but that's not really right? It's not at the same time. It's just the question doesn't make sense while it's in the air. In the same sense, these quantum things, before you observe them, they are in this weird position. So in classical computing, we have these gates. And if you take a very limited number of basic gates like OR and AND, you can build the rest of computing. Like this is universal gate set. You can do anything once you have this small gate set. And this is how transistors in our normal CPUs work. They are just doing a lot of things, but based on a very small number of gates. And you can build them physically with some electrical equipment. You can model them, simulate them. Here, for example, is an adder that uses these XOR gates and 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 OR gates to add 2 numbers. In a similar fashion, in the idea of quantum computing, in a hypothetical mathematical idea, we have gates. And they are quantum gates, and they are applied not to bits, but the qubits, quantum bits. And the difference between a bit and a quantum bit is that this quantum bit must be described in this complex way. So one way to visualize a bit is this so-called block sphere, where it's a sphere, like a planet, and from the center to the surface, there is a vector. There's an arrow, and we say that if it points directly to the North Pole, it's a 0 state. If it points directly to the South Pole, it's a 1 state. But it can also point anywhere else on the surface. And you can imagine that if it points anywhere on the equator, so across this plane, then it's exactly in between 0 and 1. So when you try to measure the state of that qubit, you never see this weird position. You only see north or south, 0 or 1. So if it's in between, that means it has equal probability to be measured at 0 or at 1. And you can describe this qubit as a vector, like a column matrix, and then gates are described as these matrices. So you do multiplication and you find the next state after applying the gate. So you can do quantum computing on paper in the sense. So in a similar fashion, we only need a very limited number of gates in order to do any sort of quantum computing, this universal gate set. So there are many gates on this paper, but you don't need as many. These are more high-level gates. You can decompose them into smaller gates. Like you can decompose multiplication into addition. Like you don't need to have native multiplication on your CPU. And then a quantum program usually looks like this, at a quantum circuit so-called, where you have qubits as these lines, and then you have the order. So you apply some gate to 1 qubit, you maybe apply a 2-qubit gate to 2 qubits, and then in the end, you measure the state of the qubits, and you supposedly get a useful result. And there are some famous algorithms, like the Shor's algorithm. This isn't a full algorithm, it's very complex, but this is just an illustration, which can find prime factors of large integer in a time which is much shorter than a regular computer can do. This isn't because there is just quantum correlation to this math problem. It's because it's a combination of certain advancements in number theory and quantum computing. So this is a hypothetical thing which we can do if we have a powerful enough quantum computer. Another one is Grover's algorithm. It's kind of similar to that first idea that I described. It's to find a thing in an unsorted list of things with a high probability, faster than just looking through all of them. But as scientists did in the 50s and 60s, and as many in the industry think today, the most beneficial applications of actual quantum computing would be to simulating quantum things. Because it would be amazing if we could develop new drugs and new materials by simulating the actual universe instead of doing experiments and expensive prototypes. Okay, so up to this point, we only talked about hypothetical. Like if you could have this kind of qubit, and you can operate it, then you can maybe solve these problems and apply these algorithms. Those algorithms were developed before any sort of practical quantum computer existed. So how to build one? This was the most mind-blowing thing to me, at least. I thought, well, you need these electrons or photons or some quantum stuff, right? But it turns out not necessarily. You just need to have something that behaves in a quantum way, that behaves like a qubit. It's not necessarily an electron or some small thing. It could be a big atom even. Or it could be a thing that has nothing to do with these small things. So these are some of the approaches that you can build quantum computers. Some are actually practical, and some computers are built. Some are hypothetical. And I want to focus on the one that my company is working on. Most of the companies that make progress today work in this area. It's called superconducting quantum computer. So forget about small electrons for a minute. Imagine a simple electrical circuit with wires. There's an inductor and a capacitor, and these are just the things that can hold energy in different forms. And if you have that wire and then you apply some energy, that energy starts basically circulating because it's a loop. And it turns out, in certain conditions, this kind of acts like that qubit, like a quantum thing. In one of the approaches, the direction of the current is considered a state. So if it goes counterclockwise, it's 0. If it goes clockwise, it's 1. But it can also, under certain condition, be kind of in this two states at the same time, going this way and this way. But actually, it's the wave. It's the probability distribution of finding the current going this way is some number, and finding the wave, the current going this way is another number. The problem with this approach is that there is resistance. So if you start doing this, there is resistance in these wires, and the energy dissipates, and you actually lose information. So that state is lost due to loss of energy. The solution to there is that first word, superconducting. Turns out certain materials experience a phase shift once you cool them down to near absolute 0, and their resistance suddenly goes to almost 0, essentially none. And if you build the thing out of this material and you cool it down to almost absolute 0 and you apply energy, it starts going there almost infinitely. We still have a problem, though, because if you have that thing, okay, it goes there, it's a qubit, but the energy levels that describe this thing are uniform. That means that you apply some energy, it goes into another state. You apply the same energy, it goes into even higher state. And we don't want that. We just want basically 1 and 2, or 0 and 1, 2 states. We don't want more states, but there are more states because this thing is just a quantum thing. In that electron example in the beginning, the problem was solved naturally because that thing has unharmonic energy state. So if you apply the same energy again, it doesn't go higher, nothing happens. So we want the same, and that thing is solved by so-called Josephson junction. It's basically a thin layer of insulator between the superconductors that, among other things, create some crazy tunneling stuff. But in the end, you get this unharmonic energy levels, and you can isolate 0 and 1. And in practice, it looks a little bit like this. This isn't our chip, but some prototype from MIT, where a qubit is actually this tiny circuit, and then these kind of wires going there are the things to which you apply energy in order to change the state, and also from which you can read the state in the end. And in reality, it looks something like this. You don't have to read all the text, but this is that chandelier thing that you often see in quantum computing things. It's basically just a bunch of wires going from top to bottom. And in the end, there's this quantum chip, which is usually quite small. And all these things are needed because you have to basically connect that tiny thing to a bunch of outside electronics. But that tiny thing should be at almost absolute 0, like millikelvin above absolute 0. So this thing has multiple chambers, and the temperature goes down from room temperature to that low temperature. This is a picture of one of our systems where at the bottom chip is somewhere inside, and then all the wires and other components are just going to be connected to there. And together, when connected, that golden chandelier thing goes into this white refrigerator. It's sealed, it's vacuumed, it's isolated from the rest of the universe as much as possible. There are magnetic shields and other things. You have to make this thing not interact with the rest of the world. And then there are pumps to heat this very cold gas, and some electronics and software running on it. So I have this picture that describes kind of the full stack journey. If you want to actually run something like this quantum circuit on a quantum computer, what has to happen? And I'm going to zoom at different places. So we start with this idea that we have that algorithm in our mind. We maybe hypothesized in the 50s, and now we can finally write it as a quantum circuit. We write it as a quantum circuit, and then the first thing that we have to do is transpile it into those gates that our computer supports. As I said, this is equivalent thing. We don't have to implement all possible gates, but we have to have the rules of transforming some gate into a set of gates that our computer can run. So this transpilation happens, and then this is still just a mathematical thing. It's a description of gates. We need to convert it into actual pulses that will be sent to these chips, the actual electrical pulses. And in order to do this, we use another piece of software called the compiler. It's one of the compilers. It's circuit-to-pulse compiler that takes these gates and then looks at the current state of the quantum computer, looks at what kind of frequencies those qubits would interact with, and generates basically something that looks like an audio file, where you have multiple channels, maybe stereo with 2 channels. In this case, we might have 5 channels because we're working with 5 qubits. And for each channel, there's a description of what kind of wave to apply, maybe wait, do nothing. And it's all synchronized in time so that it has to be running together at the same time. So you convert the circuit into description of the waves. And then another compilation part happens where we need to now convert this basically audio file into analog signals, actually be sent to the instruments. These signals are uploaded to the instrument memory, and then the instruments fire up at a certain time and apply all these things in synchronized fashion. And they have to be extremely synchronized, like to nanosecond precision, to the point where when calibrating these instruments, the people who do that have to take into account the length of the cables. Because of the speed of light that goes on the cable, a certain longer cable would have to make you delay some signal or stuff like that. So you apply this on the chip, and then another instrument reads the state of those qubits on the chip, gives it back to that high-level software, and we basically take the journey back. We have to convert this into numbers, and then we convert it into the representation that that user would like to see when they think about their qubits. And unsurprisingly, this whole thing, this whole industry is mostly Python. It's the same story as with AI and machine learning. There are a lot of scientific tools in Python. There are a lot of math and quantum computing libraries and lots of scientists. And all of them use Python. And most of the quantum computing companies develop some sort of Python ecosystem. We have our own, and we decided that the quantum computers that we sell must be compatible with the most common ones. So you can use, for example, this Qiskit developed by IBM or Cirq developed by Google. You can use those to develop your circuits, but then you can use our software to convert this into the thing that can be run on our computer. OK, so hope I have time for a demo. Let's see. So we have this cloud quantum computer, actually 2 of them. And we're going to work today with this 20-qubit one. So this describes the topology. You don't see on this screen very well, but there's not enough contrast, but some of them are connected. So this is a physical connection of the qubits on the chip. They are connected with the wires. And let's do this. Here, I use Qiskit here, but I can use some other library. And I made this circuit, and I didn't apply any gates. I didn't do anything. All I do is measure right away. So what do you think will happen if I measure all the qubits without doing anything to them? I have 4 qubits, by the way. The thing that would happen is that, well, it depends on what those qubits begin with. What kind of state are they in the beginning before we do anything? And usually these quantum computers, they try to do that. The qubits are initialized at 0 state. So with the highest probability, all of them should show us 0. And this might take a while. By the way, here, when running this job, I set shots 1,000, and this means please run this circuit 1,000 times and give me the probability results. So these are the results, and when I visualize them, most of them say 0, 0, 0, 0. That means in most cases, all the qubits measured 0. Now, I will change this circuit a little bit and apply this so-called Hadamard gate. And this gate takes a qubit and puts it into a superposition. So at this point, this qubit should be one qubit, the first one. It should be equally probable to be 0 or 1. And if I run this again, I will hopefully see that result. So the qubits 2, 3, and 4 will still be at 0. But the qubit 1, in half the cases, should be 1. Half the cases should be 0. Maybe I should reduce the number of shots, because this takes a while. The funny thing is that the actual execution with this nanosecond precision thing, it literally takes like a fraction of a second. Everything else is the overhead. So we have transformations, we have Python runtime, which isn't the fastest, we have network, we have serialization, deserialization between these components of the software. But in the end, the execution on the chip is ridiculously fast. So while it's working, maybe I'll just show you a this result would be if I run Hadamard on all the gates, on all the qubits, sorry. OK, we have the result. So as you can see, most common results are all zeros, or all zeros and that first qubit is 1, which makes sense. And now let's do this entanglement thing. So I have some code prepared. What I do here is I put the Hadamard gate, sorry, this should come last. We want the measure to be almost always last. So I put the Hadamard gate on the first qubit. This makes the first qubit to be in between 0 and 1. And then I apply the CX gate. That means it's the gate that changes the state of another qubit if that first qubit is 1, and doesn't change the state if that first qubit is 0. So this way, we entangle the state of the second qubit with the first qubit. And then we do it with 2 more qubits. And now, in theory, if you do this on paper, what you should see is, well, it's either all of them are 0 or all of them are 1, because it's all based on the first qubit. And hopefully, we will see exactly that. But in all the previous runs, you saw that it's statistical. Like, it's mostly there, but there is some noise, some errors. So here we also see that. In theory, if you do it on paper, it should be exactly 50-50 on all zeros and all ones and nothing in between. However, quantum computers are not there yet, and there's noise, and there's calibration errors, et cetera, et cetera. So we see a result like this. This may be not the most representative result, because this isn't like the best chip ever and not the best state of the calibration. These things change over time. If you don't touch it at all, then it can just drift away and become worse and worse. So you have to recalibrate it sometimes multiple times a day. Most of these things are specific to the superconducting quantum computers. Other approaches to building a quantum computer have other benefits, but also have disadvantages. All right, maybe the last thing, I'm not sure if I'm okay on time. Usually, most of the people that use quantum computers today are researchers, and most of the organizations and companies that buy it is not because they want to, simulate a new battery. You cannot yet, but because you want to learn more about quantum computing and maybe incorporate it into your research or products. So for most users today, just having circuits is not enough. They want to have circuits and then control something that happens. Like, they want access to the assembly language and to the motherboard, basically. So one of the things that our company does, and many others also do, is offer a set of software packages. So if you buy a quantum computer from us, and if you want one, talk to me, I can give you a discount. It's about, I don't know, 40 million. But you get also lots of software to operate it on a very low level. So one of the pieces of software is that you can still run circuits, but then you can control the way it's converted into those pulses on different levels and maybe do something unusual. One of the things you might want to do is to see how stable is the qubit. They are not stable. Like if you put it in a state and wait a second, it's gone. It's even if you wait a millisecond, it's long gone. The state is not there. So one of the issues with these circuits is that, okay, I have an algorithm. There are 50,000 gates, but if I just run them, I don't have enough time. By the time I get to the 10% of execution, the whole quantum state is gone, and now I have just random number simulator. So what you might want to try to measure is how long it takes for a qubit to decohere, to lose its state. And one way to do this is you take a circuit, you apply some gates that put the qubit into a certain state, known state, and then you wait a little bit and you see the state. Then you wait a little bit more and you look at the state again. And you do this with different number of waits. And you see, maybe you graph it like this, how over time your state goes to garbage. So this isn't, by the way, the cloud thing, because you cannot do this on the cloud yet. This is one of the internal research stations at the company, where you just look at certain qubit and you want to see how fast it decoheres. And with certain software that allows this experiment automation, so-called, you can do things like this. So I think this was mostly what I wanted to say. Thank you very much. If you have any questions, I'll be happy to try to answer them. And I have some resources if you want. And this is like the best quantum meme I could find.
A very good meme. Thank you very much. We have a few questions here on the Discords. First one is, what are some popular Python libraries for quantum computing, and how do they differ? For example, Quickset, CircQ, PennyLane.
Yes. So these are some of the most popular. Probably if you talk to scientists, most of them are the happiest with Qiskit. It's the most feature-rich. It even has a simulator. It even has a simulator of IQM chip. So we can get a Qiskit package called Qiskit on IQM, which is like Qiskit plus our specific code. And you can build circuits there, and you can simulate a 5-qubit machine there with a relatively close proximity. Circ is probably the second one. It has some advantages, and it's a bit easier to work with, maybe, but it has fewer features. So if you want to try do things just on your computer and look at these circuits, build these circuits, and see how they maybe transpile, decompose, etc., Qiskit is probably the easiest to start with.
You mentioned some of the algorithms for trying to find large primes, and I'm curious of your thoughts on if quantum computing will actually break all the modern encryption or not.
Yeah. Yes and no. So will quantum computing break encryption? We're going to learn now. No, I'm kidding. I have somewhere. Oh, I gave a talk titled like this that talks exactly about quantum encryption or encryption, and then how to use quantum computing to possibly break it. So yes, if you only look at certain encryption algorithms that are based on prime factorization. They're based on the fact that if you take 2 prime numbers, multiply them, it's very easy to do, and you get this huge number. And if you want to find out which prime numbers were used to multiply it, it's very hard to do. With a big enough number, it will take like years on a regular computer to do. In theory, with that Shor's algorithm on a quantum computer, you can do it very fast. And if I had a very good working big quantum computer right here, I would like decrypt most of your traffic. But there are other algorithms. And there are actually a specific field of research called quantum cryptography that takes into account this and actually uses the quantum properties in order to do cryptography that is quantum breaking safe, or still hard to break even with a quantum computer. So quantum computers will break encryption and create complete chaos and the end of the civilization if it happens suddenly. If like suddenly tomorrow someone has a working million-qubit quantum computer. Yes. But this will probably not happen, and many countries and many organizations go there slowly, so we know the pace of progress. So if we see that there is a risk that this is happening, then we will start probably switching to different modes of encryption so that when that happens, we don't kill each other.
Very good answer. Thank you. Question here is, how can a normal software developer work with quantum computers and write algorithms? Like, is there perhaps a open source repository you can share?
So actually, there are lots. Usually, these companies try to do something to educate. So you can start with something like this. At IQM, we have IQM Academy, a set of interactive online courses where you can learn about these things and actually like build circuits like this. It's very good. So this is one way. You don't have to know quantum physics. You don't have to have any PhDs or math. This is approachable to everyone. And then you actually see how to do this in actual like Python libraries, etc. There are lots of courses and books. If you want to learn a bit about quantum, like underlying things, I have some resources like this is a great book about the history. It's not just people's and dates. It's a bit technical. And then there are really good books by Sean Carroll, and he also has a podcast. And in one of the podcasts, like this episode 275, he described this quantum thing really well. And he addresses many myths that people have about quantum. Like the universe is pixelated. There are these, if you zoom in, there are these little pixels. The quantum is not about, quantum mechanics is not discrete. Nothing in there is discrete. All the equations, all the things that describe the waves are continuous. It's just when you solve them, you find these discrete patches. But anyway, this is for the like background. And as I said, there's IQM Academy. There's IBM learning thing, also similar thing. And there's amazing website called Quantum Country, which also talks about these quantum computing theory and gates with a bit of math. But it's interactive in a sense that it tries to explain things to you and then tell you to come back over time to do the space repetition thing so that you actually understand it. So if you want to get into it, if you know this, if you would learn this, you would be like in the top 1% of candidates for hiring at quantum computing companies. Because all of them need software developers. We actually also need them. I mean, we're still hiring. So if you want to get into this space, it's an interesting space. Even though some people would say maybe this is unachievable, like we will never get a quantum computer big enough, maybe. But it's still an amazing journey, and it's interesting to work on this stuff.
Thank you. As you saw, or as you showed in the demo, that the result is unstable. How are you able to test the results and make sure that they are correct? Just throw larger and larger numbers at the shots, or something else?
Yes. So testing is done like you can imagine. Like you have a certain theory how the system should behave, then you actually build the hardware, run these things, and you see the correlations. This is again where Python usually helps, because many Python libraries for science have this thing called fitting, where you have a function which is perfect, like the shape which you would expect from the theory, and then you take the results from the actual execution, and it's this patched around this function, and you could kind of enumerate how close is the result to the hypothetical. If it's really close, then your system is really good. It's really well calibrated. If it's far, maybe there is a heating issue. Sometimes, a temperature goes to 1 Kelvin, and it's just garbage. So in a sense, it's similar to how you can imagine hardware testing when the hardware is unstable. Mm-hmm. I'm not sure if that answers it in deeply, but...
There's one more question here. What role does the AER provider play in QuickKit, and how do you simulate quantum circuits using it in Python? Maybe you've already answered the question, and perhaps you want to answer in Discord afterwards, but please.
Okay, I couldn't hear the first part, I'm sorry.
It was the role of the AER provider.
Yeah, okay, yes. So AER is that thing in Qiskit which allows you, among other things, to build a model of your quantum computer. And this is what we use to build kind of simulated version of our chip. So it's not the simulated part that we have, it's not an alternative to this AER, it's using that AER model. And we apply our custom so-called noise model, which describes how our particular chip operates in good conditions.
Thank you. Do we have any questions on this? So we get a mic to one of those.
Thank you. Nice meme, by the way. Question, is there any practical applications already using this, like Python and quantum computing?
Short answer is no. It's scalable. Like, right? You can apply the Shor's algorithm, for example, to, it works. You can factor a number. It just happens to be, at this point, that number is small. Like, you don't take a billion-digit number and find prime factors. You take, like, a small number, and you can find prime factors. At this point, it's at the stage where you would do the same on a normal computer by just iterating all the possibilities, and it will be faster and cheaper, because I can do it on my watch, basically, now. But if I imagine scaling from, well, at the industry, we're now at the range of hundreds of qubits, physical qubits. If we scale this to a few thousand, we already might see some applications, even with that framework, where on a computer, normal computer, it would take a very long time. But computationally, you have to understand that computationally they are equivalent. There's nothing a quantum computer can do that a classical computer cannot. It's only a question of resources and time. So yeah, there's a lot of hype, understandably, about this. So people say, yeah, quantum computers, applications in portfolio management for finance and finding the best routes on the map and stuff like that. It's all there, in theory, with large enough quantum computer. But for now, we're not there yet. But the movement is quite amazing. If you compare 20 years ago, there was basically nothing. And now, well, at least I can do this demo. And it's just 20 qubits. There are chips with more than 100 qubits.
Thank you. And we have one final question.
Thanks for your speech. It was very interesting. You mentioned that you have to recalibrate the chip multiple times a day. How do you know when that needs recalibrating, and how do you do it? And do you think this is a problem?
Yes. So it's definitely a problem. It's a problem for all quantum computers of this, this architecture. How do you know when to recalibrate? When you start getting garbage. So if I would stop recalibration that automatically happens on our cloud computers and just redo this demo tomorrow, I will have more noise there in the results that I don't expect. And if I wait for a month, I might just have complete randomness. Maybe not a month. It doesn't go that bad, but it goes like worse. So you run tests. And usually we not always run tests all the time because we already know that it's better to recalibrate maybe twice a week or something. It all depends on the chip. There are many variables. When you manufacture the chip, there could be imperfections. You have some target frequencies that you try to do these qubits, but the result always is a bit different. So you have to then, after manufacturing the chip, you have to do some experiments to determine what actually you baked. And then, as I said, over time, these values just drift, sometimes due to temperature, sometimes just by itself. So yeah, the short answer is you know, when you see that it's garbage.
Thank you very much
Thank
for
you.
your talk. I have this gift bag for you.
Thank you. Thanks.